Alright, we've been talking about inductance. I've got an example here of our good old friend, the coaxial cable. And so in this example, we're going to determine the self-inductance of a coaxial cable of inner radius A and outer radius B. So I've got this figure here in the axis. This of symmetry is the z-axis, and I've got a current going up in the inner conductor I, and then the equal and opposite current going down on the outer conductor. And so why is that? Well, that's the normal operation of a coaxial cable. It carries the same current, just the polarity is reversed on the outer conductor. Alright, so we want to figure out what the self-inductance of this thing is. And we're actually only going to calculate the self-inductance in the region where the radius is larger than A but less than B. So in the middle there. We're going to ignore anything in the very center. Okay, so we're only going to consider this region, and actually we've calculated the flux density in this region before in a coaxial cable, and we found it to be this thing here, the permeability times the current I divided by 2 pi times rho in the phi direction. Remember that? And that's okay. So you might want that on your note card, or you bunny ear it in your textbook, or what have you. But you certainly don't have to memorize that. Alright, so we found that in a previous example, and that's going to be related to the self-inductance, right? And so the next thing that we need to know for the self-inductance is the flux linkage, which we're calling lambda. And that is defined as N, which is the number of turns, or the number of coils, times the flux through each coil. Alright, well, I'm looking at this coaxial cable and I said, what coils? What are you talking about? Well, if I is in the inner conductor and then the equal and opposite I is in the outer conductor, then there's an implied, at some point these things need to touch, right? At some point, so that the current goes, back this way, and way out here it has to go like this. Okay, so there is one loop. So this is the tricky part with calculating the inductance of a coaxial cable. You have to understand there is exactly one loop here. If the inner conductor carries current I and the outer conductor carries equal and opposite I, then there's an implied loop there. N is equal to 1. Okay, so our flux linkage is just equal to the flux through that loop. Okay, so now we're in business, and so we're going to calculate the flux through that loop, and here is our surface area S, right? And so we need to ask ourselves, in order to compute this surface integral, right, b dot ds, we need to ask ourselves again, when we deal with these kinds of integrals, we need to ask ourselves, what is changing in this surface area? Well, we've got rho, certainly. We've got rho going from A. I guess I should have drawn it up here. Not on the z-axis, but it starts at A. Rho is equal to A, and it goes to B. So here's rho equals B. Here's rho equal A. So it's actually this area that I'm talking about. And so rho is going from A to B, and then we're going from Z. Maybe this thing has a length of L, and so we're going Z equals 0 to L. Okay, so that's what's changing, rho and L. So we're going to integrate the flux density, like this, mu times I, over 2 pi rho. Okay, and then again, what is changing? Well, rho is changing from A to B, and Z is changing from 0 to L, or whatever the length of this thing is. And then because it's in the phi direction, right? And remember, the surface element, when phi, or when rho and z change, it's d rho dz a phi. And so when you dot ds with b here, the a rho, or the a phi time dotted with the a phi is equal to 1. So we're left with this inside the integral, right? And rho, we said rho is going to go from A to B. And z, we're just going to say, for right now, is going to go from 0 to L. And at the end of this, we might choose to get the inductance per length. And so then we'll just divide by L, and L will drop out. So this is what our integral is for right now. And so I've got a rho there, and everything else is constant here. And so when I integrate with respect to rho, okay, I've got essentially 1 over rho, and the integral of 1 over rho is natural log of rho, and then I'll plug in b and I'll plug in a, and then I'll use a property of logarithms. Natural log of b minus the natural log of a is the natural log of b over a. So this turns out to be mu I over 2 pi times the natural log of b over a dz. And notice there are no z's in there. That's nice, right? So that's all a constant as far as z is concerned. And so then I just can tack on. I can just tack on an L then, do the integration. And so I've got natural log of b over a times L, times the length of this thing. Okay, so what does that have to do with inductance? Well, we defined inductance, or we found inductance was the flux linkage over I. Okay, so we said the flux linkage, there's exactly one loop. The flux linkage is just the flux, which we've got now, right, divided by I. So then, the I's are going to cancel, and we're left with mu over 2 pi times the natural log of b over a, natural log of b over a, times L. So that's the inductance, and maybe this thing is infinitely long or something, and we want the inductance per length. So the inductance per unit length would be capital L, the inductance divided by L, and so that would be, I think we've used L prime in this class before. So L prime is the inductance per length, and that would be mu over 2 pi times the natural log of b over a.